All right. Welcome back to AP Physics C Mechanics. I'm Mr. Frensley, and we're going to do some more simple harmonic motion today. All right, today is going to be a very drawing graphs heavy day. So you got a pencil, piece of paper, a couple of pieces of paper. We're going to be drawing some graphs here. Now, this one's going to be really P1 friendly. So if you want to invite your Physics 1 friends to watch the rewatch or whatever it is, this is going to be good for them too. This goes across both subject areas. All right, first a warm up. Now, this is the only part that's not going to be really Physics 1 friendly right here, because it's going to involve some calculus. So we got a position. It's x equals a cosine omega t plus phi. T is the only variable. Well, a and the omega, that's the W, right? Looks like Peter Griffin's chin from Family Guy. It's not a W. And then phi, which looks like somebody really tried to draw Q, but just didn't want to pick up their pencil. Those are constants, right? T is the only variable, and x, of course. What would be the function for velocity? What would be the function for acceleration, right? And then now suppose that we have an object, it's mass m, it's connected to a spring, so the only potential energy is 1/2 kx squared, right? That's spring potential energy. If the object stops and reverses direction at this specific location, x equals a, what's the fastest speed that the object can attain? So 1 is calculus, so if you're watching from P1, don't worry about it, but 2 is a good one for you too, all right? So I'm going to give you a couple of minutes, take a little attempt at it. All right, on your mark, get set, try. All right, hopefully that was as much fun for you as it was for me, right? Okay, I'm only going to do number one right now. Number two is going to appear later on in this discussion, so sit tight. So number one, you got your position function. How do you find a velocity? You're going to take the derivative of the position function in order to get velocity. So first derivative gets you velocity, so we're going to look, cosine, bam, derivative, negative sign. So you're going to whip out that negative and you're going to switch the cosine to sine. But the chain rule is going to come along and say, whoops, the inside is more complicated than all that. Multiply by the derivative of the inside. So derivative of omega t plus phi, omega is a constant, phi is a constant, t to the 1 power, derivative is omega. So we're going to jump out on omega right here. So v is the same as x, but you got to flip the sign, the cosine to sine, negative because the derivative cosine is negative sine, jump out an omega. All right, all good. Now let's take another derivative here. So we got another derivative to get acceleration. So bam, sine turns into cosine. Still negative because when you take the derivative of sine to cosine, it doesn't change the SIGN sign. Isn't that crazy how SINE and SIGN are the exact same sounding word, and yet I have to use them interchangeably? Isn't that ridiculous? Oh, chain rule's going to come along again. He's going to bust out another omega out in front, right? Okay, so there's your acceleration. So you may have to do this on the AP exam. Don't freak out about it. All right, no biggie. The second part we're going to talk about a little later. Now, what we want to do is we really want to talk about how to represent these quantities in simple harmonic motion, your friend and mine, displacement, velocity, acceleration, momentum, net force, kinetic, potential, total energy, all these motion-related quantities that we learn in the first 3 units of mechanics. We want to be able to express them both in terms of equations and in terms of graphs versus different independent variables, right? So we're trying to just do multiple representations here. That's all we're doing, right? All right, let's review from last lesson. When an object oscillates, scary big word, right? It repeats its motion between 2 endpoints, okay? Simple harmonic motion is a special type oscillation. It's got our special properties. Let's see if we can remember them. Force directly proportional displacement, also opposed in direction displacement. Potential energy is a quadratic function of displacement. The endpoints are an equal distance from the equilibrium. So the distance from equilibrium to endpoint is called amplitude. The graph of displacement versus time is a sine, cosine, one of the wiggly ones, right, with the smooth edges, right? And then the period, this is the big one, is independent of the amplitude, right? That's what really makes simple harmonic motion simple. Now, let's talk about what you need to know in terms of relating all these motion quantities together, right? So you see this animation right here, and I've got 3 objects in simple harmonic motion. The first object on the left has a blue position or displacement vector pointing toward it. So x is displacement, just points from the origin, which is the red line, to wherever the object is, all right? Green velocity vector here on the second one, and you'll see how the velocity vector changed with time. We also have an acceleration vector right there. Here's some bar charts over here on the side for kinetic, potential, and total energy. All right, so no big deal. You can see what's going on in this here diagram, right? So here's what I want you to do. I want you to look at this animation, and I want you to make a list. Which of these quantities is the biggest number at equilibrium, right? And don't worry about the sign, okay? Just the biggest magnitude number, okay? So of the quantities, position, velocity, acceleration, force, momentum, kinetic, potential, total energy, whatever you can think of, which ones are the biggest magnitude number at equilibrium? Which ones are 0 at equilibrium? Which ones are the biggest magnitude number at the endpoints? Which ones are 0 at the endpoints? All right, so I'm going to give you a couple of minutes. Let's say I want you to maybe make a T-chart or something on your paper, you know, max, min, equilibrium, endpoint, and see what you come up with. Think of all the quantities you could fill in that little T-chart. All right, on your mark and set, go. Okay, that song would have sounded a lot better if both stereo channels came through. It didn't quite work out the way I wanted it to. Okay, let's talk about this. What is going to be the biggest magnitude amount at the equilibrium position, right? So at equilibrium, we're going to have the biggest number, speed, magnitude of velocity. It's where the meters per second are the most, is on that red line. Okay, the momentum, well, momentum depends on velocity, right? So when your velocity is the biggest magnitude, so is your momentum. And then, of course, what else depends on your velocity? You got it, kinetic energy. So those things are going to be the biggest numbers in terms of magnitude on the red line, which is equilibrium. All three are zero at the endpoints. All three are zero at the endpoints. Now, at the endpoints, we're going to have a lot of displacement. Duh. Okay. Yeah. Duh. Displacement is the most at the endpoints. That's where you're displaced the farthest from equilibrium. But also notice the acceleration is the greatest at the endpoints as well. The acceleration is always opposed to the displacement and directly proportional to it. So the bigger the displacement from equilibrium, the more acceleration is trying to get the object to go back to equilibrium. Why? Because there's more net force. There's a greater net force. The farther from equilibrium, the harder the force is trying to get you back to equilibrium. And then you might have noticed from the bar charts that you also have the most potential energy at the endpoints. So at the endpoints, all the energy is potential. Equilibrium, all the energy is kinetic. That's going to be worth remembering here coming up. Okay. Now, here's what we're going to do. What we're going to do is you're going to draw 8 grids that look like this on your paper. 8 grids that look like this, numbered from 0 to 8. You're going to label them X versus T, V versus T, A versus T, F versus T, P versus T for momentum, U versus T, K versus T, and E versus T. So you got 8 of these you owe me, okay? Now I'm going to flip back. I'm going to give you your 2.5 minutes again. All right, 2.5 minutes to draw them. All right, you got all those grids on your paper because you're about to draw more wiggles than an Australian children's entertainment group. All right, put this one down for position versus time. Draw that one right there. Sketch it. The period is 4. Sketch it exactly that way. That's your position versus time graph. Are you ready? Now here comes your task. You're going to draw all 7 other graphs, and they need to be consistent with this position versus time graph. So the velocity graph has to look like the derivative of the position graph, and so forth. Are you ready? Are you excited? I know I am. So here we go. Here's your time to draw all 7 other graphs. Okay, I'm totally answering texts from my fans while y'all are drawing graphs. If you'd like to reach out to me, it's 1-800-555-AP Physics C, Mechanics and Electricity and Magnetism, and my extension is the square root of 42. All right, so let's see. Is this what you drew? So what you can see here is I have my magical bouncing ball here, and you'll see I even have my nifty acceleration and velocity vectors right along with it, and my nifty spring. Ooh, look at it stretching out. You're getting sleepy, very sleepy. I hope you're not getting sleepy during this. So here's a position graph. I asked you to make it a cosine function. It starts at the one end point. It's got the period of 4 seconds like you see there. Draw 2 cycles, all right? All good. Now, so the position function is a cosine omega t. So if you are calculus enabled, which I hope you are for AP Physics C, then you would say, all right, the velocity function would be the derivative of that, which would be the derivative cosine is negative sine. You're going to pull out an omega, but this is just a sketch. So one of the things you need to know on an AP exam is if they ask you to sketch a graph, they are really not looking for anything specific with like heights and numbers. Like you might look and say, well, the velocity must be bigger than the position function because it got multiplied by omega. Yet they just want to see what the shape looks like. So you would say, all right, what's negative sine look like? Well, we start at 0 and we go down. Now, let's say you're not calculus enabled. Let's say you're a Physics 1 student. Then here's what you would say. Physics 1 student would say the slope of a position graph is velocity. We start with 0 slope at the beginning. That's 0 velocity. Then the slope is very negative at time 1. That's a very negative velocity. 0 slope at 2. So 0 velocity at 2. Positive slope at 3. So we have a very high up velocity at 3. And then 0 slope at 4. So we have 0 velocity at 4. And then you just repeat. Right? So remember what we said, the reason why simple harmonic motion is the simplest repeating motion is all the graphs have the same parent function. They may start at different parts of that parent function where x starts at the endpoint and velocity starts at 0 and a starts at the most negative it can be, but they're all the same parent function. If you're calculus enabled, you might have said, hey, let's take another derivative of velocity to get acceleration. Take the derivative of negative sine, you get negative cosine, and you would have sketched a negative cosine graph. For my students in P1, you would have said, well, the velocity starts with a very negative slope, very negative acceleration. The slope of velocity is acceleration. 0 slope of velocity, 0 acceleration. Positive slope at 2 for velocity, positive acceleration. 0 slope of velocity at 3, 0 acceleration. Negative slope of velocity at 4, negative acceleration. And notice, acceleration is high and low at the same time that position is high and low, but the opposite, right? High displacement, positive, big negative acceleration, and vice versa. On the other hand, velocity is 0 at the same time that x is at an endpoint. Velocity is the most positive or negative at the same time that x is at 0. So this is just another way of saying what we said on the previous slide where we were saying who's maximum and minimum at endpoint equilibrium. All right. Potential energy. Oh, let me just make a note here. The velocity and momentum graphs would look exactly the same because momentum is mass times velocity. So if you ever take a quantity such as velocity and multiply it by a positive number, then the result, momentum, will have the exact same looking graph. It might be stretched or shrunk. You deal with that in your algebra teacher. Okay, that's not for me. All right, it's just the same looking graph. Net force has the exact same look as acceleration. So if you made your momentum and velocity graphs look exactly the spit and image the same, good job. If you made your force and acceleration graphs look exactly the same, good job. Okay, potential energy is 1/2 kx squared. So when am I going to have a lot of potential energy? Well, when x is a lot of x, 1/2 kx squared, a lot of potential energy. 0x, 0 potential energy. Well, that's a negative x, but 1/2 kx squared, that's going to be a high potential energy. I should probably be saying this while it's over here. U equals 1/2 kx squared. Okay, at time 3, 0 position, 0 potential energy, then a high potential energy here, or a high x. So you're going to square a big x, you're going to get a lot of potential energy. So when x is a big positive or a big negative, you get a big positive potential energy, right? Same's going to go for kinetic energy and speed or velocity, right? Just so you know, you could come up with a function for this. All you got to do is just say U equals 1/2 kx squared, and x is a cosine omega t. So you just get a cosine squared function. Isn't that delicious? Plug in v equals negative a omega sine omega t into 1/2 mv squared, and you'll get this yuck. That's pretty annoying, right? Or, you know, what you could say is you could just say, hey, when the speed is a lot positive or negative velocity, you get a lot of kinetic energy, right? So the kinetic energy is most at 1357, because that's when the speed, positive or negative, when the velocity is the biggest magnitude, right? And then when the speed, the velocity is zero kinetic energy. And if you add kinetic and potential energy together, you'll see that it's either all potential, all kinetic, or some mixture, but it makes a constant total energy. Welcome to conservation of energy. Now, I'm going to do a little bit of algebra here. So I'm going to go through it quickly, because if you need to really see it, you're just going to watch it on the review, right? Don't write it down. But I'm going to take this period equation that I got once upon a time for a spring and mass oscillator, and I'm just going to manipulate it around a bit. I'm going to bring the 2 pi down, and I'm going to flip both sides. Now, why am I bringing the 2 pi down and flipping both sides? Because now this thing right here, this 2 pi over the period, is omega. This 2 pi over the period, that thing is omega. And now what I'm going to do is I'm going to solve for the spring constant, right? So it turns out that the spring constant, if I square both sides and multiply by m, is m omega squared. So when I studied simple harmonic motion in college, I had studied it in high school, and I always knew that spring potential energy is 1/2 kx squared. But my professor in college never used spring constant. Instead, he said 1/2 m omega squared x squared, not 1/2 kx squared for potential energy, but 1/2 m omega squared x squared. And it took me like a week to realize that m omega squared was just the k that I was using, right? And then I was able to make that connection. So k is the same as m omega squared. Now, why do I care? The reason why I care is because I just said that k, kinetic energy, is 1/2 ma squared omega squared sine squared omega t. That came from plugging in v equals negative a omega sine omega t into kinetic energy 1/2 mv squared. Then I just multiplied it all out, right? Well, there's an m and there's an omega squared, an m and an omega squared. So I'm going to change that m and that omega squared into just spring constant. The m and the omega squared just turned into spring constant. Okay, all good. Now, I'm going to recall from the previous slide that the potential energy is 1/2 k x, this whole thing I'm underlining with my mouse is x squared, 1/2 k x squared, which looks like 1/2 k amplitude squared cosine omega t squared. So what am I going to do? Going to get the total energy. How am I going to get the total energy? Add kinetic and potential energy. So kinetic energy looks like this garbage pile, and potential energy looks like this nightmare. But you know what? The 1/2 ka squared is the same out in front. So I can just factor out the 1/2 ka squared. I get a sine squared omega t, a cosine squared omega t. Oh man, what are those going to make? 1. So that's the total energy of a simple harmonic motion. Frensli, you said that amplitude doesn't matter. No, I said amplitude does not affect the period, but amplitude most certainly decides the total energy of the oscillation. That's important to know. Amplitude does not get to talk to the timing, the period. Amplitude has everything to say about the total energy. More total energy, greater amplitude of oscillation. Isn't that great? So here are 3 equations for total energy for simple harmonic motion. You could calculate the total energy when all the energy is potential energy and you're located at the endpoint. It's 1/2 kx squared, but where x equals the amplitude because you're at an endpoint. All the energy is potential energy. Remember when we said that 10 minutes ago? You could say that the total energy is the kinetic energy when it's all kinetic energy at the equilibrium. So that'd be 1/2 mv squared when the v is the most it can ever be at the equilibrium, right? Or if you don't like being at the end point or the equilibrium, you can be in these little weird places in between, and you can just say that it's a mix of kinetic and potential energy at some in between point. Personally, I don't like that. I would do, if you said, hey, Frensli, go calculate the total energy of this oscillation, I would try the equations in these orders. Do I know the spring constant, the amplitude? No. Do I know the mass and the fastest speed? Okay, well, last one's the last resort, frankly. I don't like to be in those in-between places, okay? So how can we calculate the maximum speed, which is what the other part of our go-to-it was? Well, all you got to do is set the total energy equal to the total energy. The total energy at equilibrium is all kinetic. The total energy at the endpoints all potential. So we have 1/2 mv squared. That's all the energy when it's all kinetic at the equilibrium. 1/2 Ka squared. That's the total energy at the endpoints, right? When it's all potential. And so I can nuke a 1/2, and I brought the m over. So I'm just dividing by m. I'm trying to get the v. So I'm going to take the square root. And so when I take the square root, I get a maximum speed equals a, because a was squared. So you just lose the square, but the k over m is going to go inside of the radical, right? Gosh, Frensley, this K and M business being under the radical, that seems to show up a lot of places in simple harmonic motion. Yes, that's why it's simple, because it's all the same thing. It all depends on radical K over M, which, if you'll notice from a couple of slides ago, is really just this omega thing. Omega is radical K over M. So really this is V equals A times omega. That's the omega of a simple harmonic motion. Everything is connected by omega. Okay, here's what we're going to end on today. This is the final boss, okay? The final boss of simple harmonic motion. Now, before, you drew a bunch of graph grids, but all the graph grids had time on the horizontal. This time, you're going to draw a bunch of graph grids, but most of them have X, displacement on the horizontal, and one of them, it looks like, actually is a K versus U graph. Now, I'm going to reset the time, and you're just going to draw, and notice there's no tick marks. There's no, you're just going to sketch. You're just going to give me the shape. No tick marks, and let me just warn you, none of these are going to be wiggles, okay? So I'm going to reset the time here, and you're going to, on your paper, you're going to draw these 8 little grids. No, some of them have all 4 quadrants. Some of them only have 2 quadrants. Some of them only have 1. Draw it exactly like this and label it exactly like this, okay? So here's your 2 minutes. On your mark, get set, go. All right, is your heart pounding like mine is? Here's a hint. None of these are going to be sine waves. Don't draw any sine waves. 2 of them are going to be lines through the origin. 2 of them are going to be lines that aren't through the origin. 2 of them are going to be parabolas, and 2 of them aren't even going to be functions. This is your 5 minutes. Figure out what shapes they're going to be. On your mark, get set, go. Now, I know what you're thinking. There must be a lot of different graphs in simple harmonic motion. Yes, there are. And no one says that they don't cross over with other topics that might still be tested on the AP exam. So you've been warned on that. Because remember, even if simple harmonic motion isn't on this AP exam this year, springs and energy and momentum will be. All right, so you say there's a lot of graphs in simple harmonic motion. Yes, there are. So here's all of them. That's all the graphs. Look on my works, ye mighty in despair. Can you tell I wish I was doing like English literature and composition right now instead of this? No, I'm just joking. Okay. No, don't fire me. I'll still do physics. So this is all the graphs. Holy smokes. Okay, so you'll see I have my wiggling ball over here, and the timing of this animated GIF didn't come across nicely because it seems to be in an awful hurry. But you'll see that as the wiggling ball wiggles up and down on its little spring, that the graphs are being traced out by a white dot. Now, we already talked about these 6. These are the graphs with time on the horizontal. So we already talked about those. They all wiggle. They're all sines or cosines or whatever, you know, they're lookalikes, right? But I'm going to go in a different order than the ones you wrote down. I'm going to do the ones I think are the simplest first. And the simplest graph, in my opinion, was the kinetic energy versus potential energy graph. So wait a minute, what is that? That's just a line. Specifically, it's aligned with a slope of -1. Yeah, the intercepts on both ends are the total energy. Where do you get a line with a slope of -1? Let's look at this basic equation. Total energy is kinetic plus potential. Now I'm going to compare that to an equation from algebra that might be like total energy is a constant, K is the Y, and potential energy is the X. So C equals Y plus X, move that around, Y equals C minus X. That's a line with a slope of -1, and both of the intercepts are C, which is the total energy. All right, all good. Did you get that? Give yourself a pat on the head and a cookie. All right, good job. What on earth is going on here? This is the one you would never have guessed. I'll bet you would never have guessed this if you weren't taught it directly. Velocity versus displacement. And because momentum depends on velocity and is directly proportional, that would also be momentum versus displacement. So V versus X and P versus X are actually ellipses. They aren't even functions to begin with. Why? Well, there's a big derivation down here that I really don't want to bore you with, but notice what I do is I start with total energy. So the total energy at any point equals the total energy at the end point. I replace the K with the M omega squared. I did a bunch of dividing out. And then at the end, I get V squared over the maximum V squared plus X over the maximum X squared equals 1. That is the form of an ellipse. So you'll see, if you want to go back through and see this again, you probably don't have to, but if you want to watch it on the replay, you'll see my math here, starting with total energy equals the total energy at equilibrium. And notice out here, I kind of annotate what I'm doing. I plug in K as that M omega squared I talked about. Then the halves and the M's cancel out. And then when I rearrange, it looks like Y squared over the biggest Y squared plus X squared over the biggest X squared equals 1, which is the equation you might remember from your algebra class for an ellipse. An ellipse, who would have thunk it, right? Acceleration and force, both versus position, are a line through the origin. So both acceleration and force have the same graph versus position. Comes from F equals negative kx. That by itself is already aligned with the negative slope. F is the y, negative k is the slope, and x is the horizontal, right? If you replace F with ma, then you just get the same line, but with a different slope. It's negative y, a is the y, negative, and k over m is the slope. And then the X is the horizontal variable, right? So those are the lines to the origin. I'm hoping this is one that you all got. So if you got this one, then give yourself a pat on the head and a biscuit. Potential energy is 1/2 kx squared. So potential energy versus X is just an upward opening parabola, 1/2 kx squared. The kinetic energy is the flip of that. Why? Because if E is K plus U, then K is total energy minus U. That's just basic algebra. Plug in potential energy is 1/2 kx squared, and I've got Y equals a constant minus X squared. A constant minus X squared is just, an Archie parabola kind of thing, whereas Y equals something X squared is the smiley parabola. Okay, tell me you didn't get this. The total energy, it's a line. It's a line. It's a flat line. Total energy stays the same. I hope that that's not that difficult on you, right? Anytime someone asks about the total energy, it's a straight flat line, unless you have a really good reason to make it decrease, such as friction or some kind of resistive force. All right, so to summarize, at the endpoints, velocity, momentum, kinetic energy are 0. At the endpoints, you have the most acceleration, force, potential energy, and that rule is flipped at the equilibrium. At the equilibrium, velocity, momentum, kinetic energy are the greatest they can be, as in farthest from 0, and then acceleration, force, potential energy are 0 at equilibrium. Any graph of simple harmonic motion that has time on the horizontal is going to be some kind of sine graph. The amplitude is what depends the total energy and the maximum speed. Amplitude does not ever affect the period of the motion, though. Some other properties of the system affect the period of the oscillation. In case of spring and mass, it's the spring and the mass, the K and the M, that determine the period. All right, this is going to be a shout out for those of you who are still having some trouble with getting a device or whatever. So we're looking at home AP exam testing. I think they've pretty much decided that. So the College Board is trying to figure out how they can help everyone have access. So if you need some kind of mobile tools or connectivity, or if you know someone who does in order to take their AP exam, please reach out directly to the College Board, and they're going to work on some kind of a solution for you. I know that my district has figured out a way to help each student have connectivity in their home, but that's not the case everywhere. And so if you're having trouble even after working through your local school system, you can certainly reach out to the college board. All right. Well, thank you so much for watching. That's going to be it. Remember to like me on Facebook and send me a message through my Facebook page if you have any questions. Other than that, I'll see you tomorrow for gravity. Good luck.